Hey friends, MoNaCo here. Fifth lecture video on our kinetics and equilibrium unit. We're talking about equilibrium. That's the first thing we're going to start talking about in this lecture notes. So at the end of this video, you should be able to define what an equilibrium is, and there's three types of them: solution, equilibrium, phase equilibrium, and I'll check my next slide, we'll see what they are. So here we've talked about so far reactions that only go in like one direction. So A plus B makes C. Now we're going to talk about reactions that run forward and backwards at the same time. And the special term that we use for that is called an equilibrium. So reactions that occur in both directions at the same time are in equilibrium, and there's three types of systems: physical, chemical, and solution, that can establish an equilibrium. Weird thing about equilibriums is, like, when you're looking at a reaction that's equilibrium in a jar, it's kind of like nothing's actually changing. It doesn't look like anything's going on, because the forward and the backwards are happening at the same time. So let's look and see on our notes what we've got. Equilibriums are about equal rates. Okay? So some physical and chemical reactions are capable of reaching an equilibrium. Equilibrium occurs when the rate of the forward reaction, so like how fast the forward reaction goes, is equal to the rate of the reverse reaction. So if you're making product at a certain rate and you're breaking product at a certain rate, coming back the other way, if those rates are equal, we're at an equilibrium. So it's just a vocabulary term there. So when equilibrium is reached, it does not mean that the reactants and the products are equal quantities. So you got another note. Equilibrium is represented by double arrows. Sometimes it's actually a double-headed arrow like this. Sometimes it's like a sliver backwards and a sliver backwards. But usually you got an arrow in one direction and an equal-sized arrow in the other, instead of just a single one. This lets us show that the reactions are proceeding in both directions, forward and reverse, at the same time. Equilibrium is dynamic, which means that it's constantly changing or fluctuating. So the equilibrium might shift in a direction, forward or backwards, depending on what kind of stress we put on the system. Equilibrium means that the reactant and product concentrations are constant. So if I'm making a product, I'm also breaking the product, and overall at the end of the reaction, the amounts aren't actually changing. The concentrations are constant. Equilibrium does not mean that the reactant and product are equal. It means the equal rates of the forward and reverse reaction. You might have more reactant and less product, but the amount that's changing back and forth is equal. That's why it's equilibrium. Define equilibrium in terms of reactant and product concentrations. So this is when reactant and product concentrations are not changing. We don't want to say the concentrations are equal because you might have more reactant than product, but we will say that the concentrations aren't changing. Define equilibrium in terms of forward and reverse reaction rates. This is the big definition you got to know. Reaction rates for equilibrium, forward and reverse, are equal. So the rates of the forward and reverse reactions are equal. Very much so. Let's see what else we got here. Types of equilibrium. There's the three types we're going to get into. All occur in closed systems, so like a jar with a lid on it. Okay, we can't have an open system in the atmosphere because otherwise the equilibrium won't work. It's all about the equal rates. Equilibrium is about equal rates. Physical equilibrium. It involves physical changes. So like phases. Occurs during a phase change. Think of, see, bottle of soda. If I put it out in the sun, it's closed. Some of that liquid will evaporate. But then it comes up here and it condenses back down on the bottle. So if you have a half-open bottle of soda sitting there, over time you'll get little droplets of water sticking on the inside. So for every molecule that evaporates, a molecule condenses. That's called an equilibrium phase change. So examples: solid moving back and forth with the liquid. The rate of the melting is equal to the rate of the freezing. So we're thinking about maybe ice cubes in a drink at 0 degrees Celsius. For every molecule that freezes onto an ice cube, a molecule from the ice cube melts and turns into liquid. It kind of just goes back and forth in this circular back and forth exchange. Now, the other type would be what I just said about condensation, where we have the liquid evaporating and condensing at the same time inside this closed system. The rate of condensation equals the rate of evaporation in a sealed container at maybe 100 degrees Celsius if we're talking about water. Solution equilibrium occurs at a solution's saturation point. So if I'm adding sugar into my coffee, imagine some sugar in here, eventually I'll get to the point where the coffee can't soak up any more sugar. And that's when we've got a saturation point. The coffee is saturated with sugar. And for every more molecule of sugar I add in, a molecule dissolves and then recrystallizes at the bottom. That's why you get a pile of sugar sitting at the bottom of your coffee cup or your drink. The rate, again, equilibrium is about rate, of dissolving equals the rate of crystallization. So in this example, we have sodium chloride salt in equilibrium with sodium chloride aqueous. So this is an example where I had a beaker of water, added a bunch of salt to it, and sitting on the bottom. For every molecule that dissolves, a molecule crystallizes. Back and forth in a circular type manner. Chemical equilibriums are where the rate, again, of the forward reaction equals the rate, again, of the reverse reaction. So for every molecule that goes forward, a molecule comes back. The rate of breaking bonds equals the rate of forming bonds. For every molecule that breaks apart, a molecule forms back. So in this example, this is like the triple point type diagram. The concentrations get to the point where they're constant, they're not changing. So the product's concentration increases and the reactant's concentration drops until for every product that's made, a reactant breaks. So we get to this equilibrium portion of this type of graph. Let's see what we got next. So at this point, you should have the basics of what equilibrium is. It's about equal rates. Okay? 3 types exist: physical, chemical, and solution. There is no work in the practice packet, but there's some POGLs and other activities to work on here. So thanks for watching. Have a good one.